Okay, so the next paper we're going to go through is this is a GES 2 paper, and it's from June 2024. Like I said, there's a couple of difficult papers on these, and I think this is a difficult paper. Looking back on it, it doesn't look too bad, but I think it's full of typos. There's quite a few typos in some of this earlier guy's papers. This is the new examiner writing these exam papers, and he's been on since March 2023 up until today, which is March 2025. Still going after 2 years, and his earlier papers have quite a few typos in them, which make them quite difficult to deal with. I haven't really mentioned on the website, like when you download the papers, if they have typos on them or not. Maybe I should do that. I kind of just put the papers up as they were given. Sometimes in the exams, the examiners will come in and say, hey, there's a typo on question like number 5, and you can change it, which is a bit annoying. Especially if they do it right towards the end of the paper and you're already out of time and exhausted. It's a really bad time to be jumping in there trying to rework the questions. My guys said in one of the exam centers they gave them an extra 15 minutes to correct the questions, but like I said, everyone's exhausted by that point and they can't really save it. And they only do it in some exam centers, right? So the other exam centers might not mention it, might not notice it, and then when it all goes back to the SQA to get marked, they have to be lenient on the marking. So I'm not sure how that works. We can only guess. But okay, let's have a look at this paper. This is section A, and section A is actually pretty standard. It's pretty straightforward. I'm going to go through it from start to finish, but really I think the problem is in section B on this. Section B is electronics, which is pretty hard. It's one of the tougher parts of the paper. So you can see just like your regular questions here, basically on the first one, a copper sphere, dropping it through a hole, that's quite easy, cooling an object. As part 2 is specific heat capacity, cubic T equation, single object, not like quenching hot metals in steel or anything like that. Oh, it does go through latent heat as well. It goes through specific and then latent, so it melts. We've already seen this question with ice. We hadn't actually seen this question before with something like scrap steel, so that'd be interesting to look at. It is a new, novel question. It's not very difficult to do, but we just haven't seen this style of wording before. And I think it's a good one. There's no problems with it really. Pressures, gases, usual stuff. Just gotta be a bit careful if it's a double or a triple, if it's 2 points or 3 points. So we have a look at that. Big chunky, diesel equation, diesel engine equation. Pretty tough to get all the brake specific fuel consumption and everything as usual, but nothing special on that. 10 marks. I don't think there's anything spooky. Number 5 is the combustion equation, which is a simplified combustion equation. You can see it's only a line and a half of data, which is pretty good. It means it's quite easy to work with. Mass of air, yes, fine. Sometimes, oh yeah, this actually has a typo in it because it says a fuel oil consists of this much hydrogen by mass. It's completely burned in excess of air. The mass of air required to burn the fuel. We don't know how much fuel we're burning. We're going to assume it's 1 kilogram, of course, because usually they are, but it's missing that information. So, like I said, some of these papers are full of typos, which can really throw us. The most recent papers that have come out in the last couple of exam seasons seem to have, touch wood, like, no typos in them. But you understand the problem is that as you're doing the paper, if you see the typo or you don't see the typo, you're going to do it wrong or it's going to throw you. And I'll show you one in part B. Describe how vapor compression refrigeration cycle achieves cooling. Pretty standard refrigeration questions. No problems about that. This is part B, which has is electronics and naval architecture. So we'll have a look at these. The reason why this paper is so difficult, I think, is because it's got a lot of circuits in it, and the way I approach these circuits takes a bit of time. So maybe we can speed it up a bit. Some of these questions are classics, like this one here. We've seen before. It's like an old question just dropped in there. So you've done this one in training probably about 3 or 4 times. So seeing it again, the paper is really nice, really good. This is a classic as well, which either you understand or you don't. And it's kind of like a definition question, and it's quite an easy 8 marks if you can get it. So we'll go through that and talk about what happens. Then, oh yeah, look, FBIL sine theta, magnetism, nice and easy. The problem with this is that they throw in a couple of extra units like microwebers, which is not really that bad. You got to work the whole problem backwards to get the diameter of the conductor rather than doing it forwards, which I know for you guys is a little bit tricky on the algebra sometimes. Just unnecessary really. Not too difficult really by the time you've gone through GES 1 and GES 2. but it depends on how strong your algebra is. I know algebra tends to be a bit of a sticker, right? A bit of a problem. And then we got stuff like this question. Now this question is a bit of a doozy. It's a new question. The whole thing is new. It's part A, part B kind of mashed together. Part A is nothing to do with part B. They're really separate questions. It's just a little tail end question. These are the questions where we've got a copper conductor, cross-sectional area. This is resistivity. The question is on resistivity. And they're very simple questions to do. And we don't really see them anymore. I think the new guy's taken them out because the questions are so ridiculous in the past. They were like, based upon the resistance of this piece of copper and the approximation to iron wire, and I haven't found anybody who has told me a real life application for iron wire. I've been told it's too brittle and can't really be used, so why would you have it? But you take an approximation to iron wire based upon some kind of very loose approximation, like it's 7 times the resistivity of copper, and then you can work out resistance of a piece of copper wire. Those questions are so ridiculous. So like, MacGyver, Robinson Crusoe, like strapping things together kind of thing. It relies on too many approximations, really, to be realistic. So the new guy has basically ditched that question, and this is the first instance we've seen where he's trying to bring them back again. We got this copper conductor, and it gives us all the data, and we calculate the resistance of the conductor. It's not too hard, except from the units that are used, make things a little bit tricky. And for 2 marks, it ends up not really being worth it. So basically, it's just a skip on this top question. I'll go through it and explain it, and you can judge for yourself if it's worthwhile doing. But then we have simple circuits. Now these simple circuits, well, we had a previous question on simple circuits right here, so it's quite unusual to get 2 of these in a row. You could even count this as being a simple circuit, so very unusual to have 3 of them in a row. I count this one as being a definition question, because you either know or you don't, and it always comes up to be the same, and they always ask the same thing. There's no variation on this question so far. And this one as well, you'll see slight variations. He's changed up the voltages occasionally, but I think this is a classic setup. Now this is a completely new question, and he might have copy and pasted it from another past paper that he made quite recently. And the problem really with it is that in the question it says we've got a 250 volt power supply, and in the diagram we've got a 400 volt power supply. And just looking at the diagram, basically when we do the calculations, we're not going to see this data. My advice is that we should use the written information, because the question has probably been modified up here and not in the diagram, because the diagram is harder to modify. So the diagram's been forgotten about, basically. Of course, that creates 2 different sets of solutions. In my opinion, that means they should mark it either way. I don't know what they're going to do about that. Basically, it's all a black box. We can't tell how it's been marked, or the marker's comments are probably not published on these, difficult to get hold of. And the rest of it should be fine, but it's just a long process to go through all this stuff, which is a bit of a pain. Including the typo means it's a bit of a dead question. It'll probably get completely cut out from the marking. And I can see that because my guys tell me that, hey, I didn't answer enough questions to even pass the paper. I'm sure I failed. And they come back with a pass grade. And it's a pass grade across the board, like across multiple people. So you can see they've adjusted the marking by removing this question, effectively dropping the marks and reordering the number of marks that we have available. So this is what normally exam boards will do. If there's an error in the question, it's their fault. They'll remove it completely, discount the question. So basically what I'm trying to say is, if you see a typo in the question like this, you're investing time into something that's dead. Like, it's not going to be used. So use your time to do the other questions if you see the typo. The problem is we don't see the typos because we're in a rush and we're stressed in exam conditions. So you just don't see this stuff come up. But I'll go through it. I guess I'll use the 250 volt power supply rather than 400, I suppose, right? Then the rest of it's pretty standard, I think. Solid wooden board, fully submerged. What's the total mass could be supported without it sinking? A bit of buoyancy, no problem on that. And then we've got a tough, like a slightly harder naval architecture question, but it's not too bad. We're just filling tanks with heavy fuel oil, and as bunkering some fuel, and as change of center of gravity. Not too bad, pretty standard. It's actually like the easier version of the straightforward. It's a harder topic, but we just built it into a table, and it's nice and easy to deal with. All right, but there's another typo in this paper. I can't see where it is. I'm sure we'll see it as we go along. All right, okay. Okay, so we're going to start on the very first part over here. Let's start on question number 1, section A. Explain why materials expand as a result of heating. Definition question, we don't need to go through those, but basically atoms vibrate, and temperature is a measure by which they vibrate, and the more they vibrate, the more space they take up. So as things get hot, they occupy more space. It's quite difficult to write these things out, but I'm not going to do it live on a video because we've got to focus on the calculations, right? Little two-point definition questions are quite easy to get. So a sphere made of copper has a diameter of this, and it's at a high temperature. Calculate temperature at which the ball just drops through the hole. So let's draw a diagram of this thing. We're talking about a sphere. This is just a linear expansion question. It's quite common, very common question actually to come up, like all these spheres dropping through holes, and they look like you need surface area or volume, but really we're just talking about diameter. I just want to get everything lined up before I go because I don't want to make a mistake on which one's which, right? So let's see. The ball itself has a diameter of 40.9 millimeters, and the hole that we're trying to fit it through has a diameter of 40 millimeters. You can see we have to shrink the ball by 0.19 mil. I'm still going to do my expansion equation. So we've got the diameter plus the expansion is equal to new diameter. Okay, the expansion is made from those three ingredients. It's made from the diameter times by the coefficient times by delta t. And the new diameter, well, we'll just keep it as new diameter. Let's list everything out nice and clearly so we can see what's going on. We've got the original diameter being the 40.19. The coefficient is given in the question. Just be careful about the zeros. Not really an issue these days. I don't really see people making too many mistakes anymore with this kind of stuff because you get through GES 1, and GES 1 has a lot of attention to detail in it, so you're quite used to it by now. The delta T is actually what we're going to calculate, the change of temperature required, and the new diameter will be just the 40 millimeters. So we're just going to plug it all into this equation and solve it. Let's see. If I just grab that equation, I can just drop it all down here, right? Let's plug it all in. So the old diameter was 40.19 plus the 40.19 times by the coefficient, which is 0.000018. Just double checking those numbers from the question. Times by delta t, which will be x, and then we've got this to be the new diameter, which is 40. The first thing we're going to do is minus off this from the other side, so we will get to do 40 minus the 40.19. This will give us negative 0.19. This is the amount of change we require. We require the ball to shrink by this much in its diameter. Here's my calculation. I'm going to multiply these together and then divide this by it, and then we're done. And this question, nice and easy. Nice and quick. I did this in my head, so let's do it on the calculator just in case. 40.19. There's my change. I'm going to divide it by these two multiplied together, so the 40.19 times by 0.000018, being careful on the zeros. Okay, I get negative 262, so that's the change of temperature required. So x is equal to negative 262.64, and this is the change because we said x is the same as delta t. It's not the final answer, because we have an initial temperature of 400, so the final answer will be the 400. Let's just write something like final temp. Final temperature will be the initial. We could write out the formula we're going to be using plus the change, and the change is negative, so we end up with 400 degrees minus the 262. And we should get the final temperature in degrees Celsius. So don't worry about the negatives and stuff, just make it work on the calculator. I'll just put a plus in there. Okay, you can actually override positives and negatives when you're doing this kind of stuff. Just make it work. So this will be degrees C. That will be the final temperature, right? That makes sense. It's not too hot, not too cold, just about right. And it will be the point at which the ball will be the same size as the hole, so really you need to cool it to a little bit lower than that. That's it. Nice, easy, 6 marks. Okay, number 2. Describe the difference between specific heat capacity of steel and the enthalpy of fusion of steel. Well, for 4 marks, that's actually worth talking about. And specific heat capacity comes from Q mac T. QMC delta T, and this is the specific heat capacity. They're basically just asking for the definition of specific heat capacity and the definition of entropy of fusion. And you see this in most papers, actually. They ask for a definition. It's quite a common question. They ask it slightly different ways to make it sound different, but it's really just the same thing. You can just answer it the same way. You just want to give the definition of what is specific heat capacity. So you know specific heat capacity is the amount of energy required to raise 1 kilogram of the material by 1 degree C, or 1 Kelvin, right? So we could write that out and say that's what specific heat capacity is. And entropy of fusion of steel is really, I'm going to use Q muck without the delta T. So fusion is sticking things together or breaking them apart, is the opposite. So it's sticking things together, it's freezing, so it's solidification, so it's going from a liquid to a solid, or vice versa. And it's the amount of energy required to bring about a phase change, to go from a solid to a liquid, or a liquid to a solid. And the difference between them, because they're saying describe the difference, I suppose, I would still write down the definitions, like the one-liner definitions for each of them. And then the difference between them is that the entropy of fusion, this is a latent heat, and this is specific heat, and or sensible heat. And the latent heat, it doesn't have a temperature change. Right, it happens over this. There's no change in temperature to go from a liquid to a solid. It's at, for example, using ice, it will be going, and water. It will be at 0 degrees C on the ice to 0 degrees C on the water, and that will be the phase change. And it takes a whole lot more energy to do that. I mean, there's a lot of differences, really. Describe the difference. What do you mean, the difference? I mean, we could say the units are different. We could say the application is different. We could say so many things that are different about it. But basically, the big difference between them is that there's no temperature change for latent heat, and there is a temperature change for specific heat, I suppose. But you could say quite a few things about it. All right. Okay. But really, just give the two definitions, explain the units, and then I think I'll get you the 4 marks. 4 marks, really. A steel casting is to be made by melting 6 kilograms of steel scrap, which is originally at 20 degrees. If the melting point is this much, determine the total energy required to melt the steel. So let me get rid of all this. We're going to be using both of these as we go through it. So this is a small modification. Again, we haven't seen this question before. It's a small modification on the melting ice question. So usually you get a question about ice, like ice is at -5 degrees C, and you've got to inject some heat into it. And the question is, what will the final state be? Will it be a liquid or a gas or a solid? And what temperature will that be? And you have to go through several stages. This is a little bit easier. We're going to take steel, which is a solid, and it's going to be at 20 degrees C. Then we're going to heat the steel to melting point. So this will be still a solid, but it'll be hot. It'll actually be at 1370 degrees Celsius. And then it's going to melt the steel into a liquid. And that's what they're asking for in the question. It says, a steel casting is to be made. If the melting point, determine the total energy required to melt the steel, and only melt the steel. So we're not going to do anything else to it. We're not going to heat it further. We could do, and you might see that on future questions, right? But here we are heating the steel, heat the steel, and this will be the specific. So we're going to use Q muck T on it. I can write that so we can read it. And then here we're going to melt the steel. So this will be latent, which is basically the same formula, but just without the delta T. So Q is equal to MC. Technically, it shouldn't be C. It should be L for latent, or entropy of fusion. But there's a whole bunch of different ways to say it. You can say entropy of fusion, or that's for there's a whole bunch of different ways to say it. You can say evaporation, condensation, probably fusion, and liquefaction, I suppose. There's a whole bunch. You'll see it in the paper with lots of different synonyms, and you got to pick them apart. But as you go through past papers, you'll get all that vocabulary. It's fine. Okay, so basically we've got these 2 stages, and we're going to have a look at those 2 different stages. I'll call this stage 1 and this stage 2. So let's calculate the first stage, where we're going to heat the steel using Q muck T. So this is stage 1. We're going to use Q is equal to MC delta T. The question is asking for how much energy is required. So you're going to need a certain amount of energy to heat this steel up. We just need to plug the data into it. And it's going to be quite straightforward. The mass of the steel, the capacity of the heat capacity of the steel, and the change in temperature. Nice, easy input. We're talking about 6 kilograms of steel. The heat capacity is given as 480 joules, 480 joules per kilogram Kelvin. And then the change in temperature is going from 20 up to 1370, so that's 1350, I think. So let's write down the change in temperature then. So we're going from 1370 minus the 20 to give us a change of 1350. We're going to plug all this in. So Q is equal to 6 times by 480. Okay, so we just plug everything into the equation. So we've got 6 times by 480 times by the temperature differential, which is 1350. This will tell us how much energy we need to heat up the steel to melting point. So calculator, 388888000. So we're going to need Q is equal to 3888000 joules. So that's what, 3.888 megajoules. Great, okay. Number 2 will be melting the actual steel. And this is going to take probably a lot more energy than we expect it to, because usually the enthalpies are huge, right? So we're just going to do a Q. I just like to use a Q mach T. Q is equal to mc delta T, but without the delta T, because there's no temperature change as we go through melting. We go from the 1370 liquid solid to 1370 liquid. So the mass is still the same as 6 kilograms. And then the latent heat capacity, or in this case they're calling it enthalpy of fusion, is absolutely massive. It's 247,000. That's a killer. So 247,000 joules per kilogram. If you look at the units, there's no Kelvin on that. We're using centigrade, but Kelvin's exactly the same in terms of step length, so it's just fine. So the calculation will be the amount of energy will be just 6 kilograms times by the enthalpy of fusion. So let's multiply these two together. So we've got 6 times by 247,000, and we got a big number. So this is 1482000. So that's 1.4 million joules worth of energy just to melt the steel. Okay, so of course the total energy will be these two combined, so we can say the total energy required is going to be the 38888 plus the other one down here. So add them up like that. So get my calculator, plus 3888000. Okay, so we've got the answer as 5370000 joules, which is what, 5.3 megajoules. It doesn't ask for it in megajoules, it just says determine the total energy required to melt the steel. So we have done that. We have got the total energy required, which is 5,370,000 joules. That's it, nice and easy. Okay, like I said, this first section is pretty simple. We get to part 3. Okay, question 3 is a gas equation. And we just have to be careful about this one just to make sure if it's a 2-stage or a 3-stage. It looks like it might be a 3-stage because, well, I don't know, just get that feeling. A volume of this amount of gas, there's a pressure and bar, temperature, is heated at constant pressure until its volume doubles. At this point, the gas cannot expand any further. So yeah, this is the 3rd stage. So continued heating causes the pressure to double. Show this pressure on a pressure volume diagram process. I could probably draw that straight away, but I'm going to leave it till last. I will do it. I'm just going to do part B first of all. I want to know all the numbers and everything and get it laid out so I can see it a bit clearer. So it looks like we are talking about a 3-stage process. We're going to use our formulas will be P1V1 T1 is equal to P2 V2 T2, and this will also be equal to P3 V3 and T3. It's not really necessary to write that in, it's just I think this one's going to be a 3-stage process, and we're going to be using Pervert equation. PV is equal to MRT, and we don't actually need this equation. You can see there's no characteristic gas constant given, so I'm not going to use it this time. It's just going to be these 3 stages here. Alright, so we're going to be using these guys. Let's see if we can list out the ingredients. We've got P1V1T1, P2V2 and T2, and then probably P3V3 and T3. So a volume of a gas is 1.5 meters cubed. It's at a pressure of 1.01325 bar. I'm going to convert this straight into pascals. So it's going to be 101,325 pascals straight away. The volumes of the meter cubed is just fine. And the temperature starts off at 20 degrees C. So let's convert that into Kelvin. So I'm going to add 273 onto it to get 293. So this is 293 Kelvin. Okay, great. The next part is it's heated at a constant pressure. So the pressure we kept the same. So this will be 101,325 pascals, just fine. Until its volume doubles. So the volume will be 3 meters cubed. And so from this we can calculate the second temperature over here. Because we got everything else about it, we can actually see that because the pressure is kept the same, if the volume is doubling, it probably means that the temperature is doubling. I'm not going to rely on that. We'll do the calculation to prove it, but I think it will just be doubling. At this point, the gas cannot expand any further, which means the volume will be kept the same. So the volume here will be 3 meters cubed. And continued heating causes the pressure to double. So that now this will go up to double this number. So let's take this this pressure and double it. So it's 101,325 times by 2 to get 202,650 pascals. Okay, and then we're going to calculate the final temperature. Calculate the final temperature of the gas. Yeah, I do expect the gas to double here. I suppose if the volumes get the same and the pressure is doubling, the temperature will double again. We just do everything in Kelvin, and that's going to be our like gut instinct about what's going to happen. But I want to prove it using numbers and calculations. I don't want to rely on that kind of stuff because it's very easy to slip up. So we're going to do the stage 1 to stage 2 to start with, and this will be P1 to P2. We'll just grab this part of the equation. This will be the equation we're using, and we're not going to include the pressure. It's not necessary. So this will be 1.5 over 293, and this is equal to 3 over x. Okay, not too bad. You know what to do is we calculate this side, and then we're going to flip that over with the x. So let's do that, and I'll do it slowly. So 1.5 divided by 293, and we get a number, ugly number, but there it is. So I could say that this left-hand side is 5.11945 times by 10 to the negative 3 is equal to 3 over x. And we're going to flip these guys, multiply up the x, divide down that 5.11. So 5.11945 times by 10 to the negative 3. I've got it still in my calculator, so really I'm just going to be doing 3 divided by answer. And we get 586. These numbers look very familiar. X is equal to 586 Kelvin, and yeah, that's doubling the previous temperature, which is what we expected, so that's great. And so this is the temperature after in stage 2, so we can write that down. We can call this I suppose I'm going to remove this x now and put in a 586 over here. I'm now going to be solving for the next temperature, which I do expect this to double again because we're doubling the pressure. Of course, if things aren't exactly doubling, I'm going to have to do this calculation. So there's no point me trying to take a shortcut right now because it's not going to help me later on if we have a different question where it's slightly different. You know, shortcuts are all very nice and everything, but I'm going to be using both. I'm using the shortcut in my head and then the solid calculation on the paper to check I'm doing everything right. So this will be P2 V2 T2 is equal to P3 V3 T3, and we're keeping the volume the same. So let's remove that. Let's get the numbers in for the pressure. Just separate these guys out a little bit because they're two separate equations. So the original, the pressure is now 101,325. The temperature is at 586. And this will be P3, which is 202,650 over the new temperature, which will be X. Same as we had before, we're going to calculate the left-hand side. So 101,325 divided by 586, and that gets me the left-hand side. So I can write that down, 172.909. It's just a checkpoint, don't really need to write it down, but it makes me feel better, so I will. And then I can multiply up the x, divide this number down. It's just to show our working, I suppose. So this will be 202,650 divided by this 172. I'm really just using the number in the calculator, right? So it's already in the calculator. I needed to do that anyway, so it's not a waste of time. 202,650 divided by answer. There it is, 1172. So this will be the final temperature now of 1172 Kelvin, which is double the 586, which is what we expected, but it's nice to see the confirmation there in the calculations. So that is the final temperature of the gas, which is what we need to calculate. So that's nice. This is final temperature. That's what we're looking for. Okay, great. And then show the process in a pressure volume diagram. All right, well, we've got all our data now. Now, we don't actually need the temperature, so we could have done it from just the pressure and volume information. Let's bring our pressure and volume information off to the side, and the question as well. The reason why I'm doing this second is because, first of all, I want to see everything lined up, but also it's a rarer question. We don't do many pressure volume diagrams. They're coming up more and more in the recent papers. Pressure is said first, so I suppose it will go over here. So let's see, pressure, and then here we're going to have volume. Let's keep the pressure in pascals. The volume will be done in meters cubed, and we're going to have 3 points on here. We've got low pressure and high pressure, so we can actually write those down on our graph. We can assume that this is 0. I can put a 0 there, and this will be the 101. Let's make a bit more space, squeeze it in, 101,325 pascals, and here's pressure 2, which is 202,650, and then the volume will go from 1.5 and 3, so same kind of story down here. We can just put 2 marks, equally spaced. I suppose we can actually make this into a very nice diagram on square paper. I wouldn't expect you to do it on square paper. I expect you to do it on lined paper. It says show the process on a diagram. It doesn't say graph it. It's just demonstrate the process, show the process, illustrate the process, or sketch a diagram. So it doesn't have to be 100% like neat or anything. It would be nice to get these approximately the same kind of size. Okay, so where are we starting from? We'll start low pressure, low volume. Low pressure, low volume will be here. This will be phase 1. Let's call this like phase 1, phase 2, and phase 3, or step 1, step 2, step 3, and then we're going to increase the volume while keeping the pressure the same. So this will be number 2 over here, and we can include the direction that we're moving in like this, and then we're going to go to step 3, which will be up here, which is increasing at that high volume, increasing the pressure as well as the temperature continues to increase. So it'll look like this, and this will be step number 3. We'll just add a little arrow to show that it continues increases, and that's it for 3 marks. Not so bad. Okay, let's have a look at the next one, number 4. Okay, number 4 is a big chunky one. It's going to be diesel engines. So a 6-cylinder 4-stroke diesel engine under test has a bore of 120 mil, stroke of 150. It burns this much fuel. It runs at 800 revs per minute. The mean effective pressure was found to be this much. That's the IMEP, right? And that's a bit strange. That's why it's a bit tricky. It's not too hard. During a torsion test meter, the shaft gave a reading of this many Newton meters. That would be the torque. So we've got our usual formulas here. We've got our IMEP, which is indicated mean effective pressure, and that's what this part is. The mean effective pressure was found to be this much. So this would normally be our area on the ticket times by the spring coefficient divided by the length of the ticket. But you see it doesn't really come up very often. Saying that, it does. You will see it on other papers. The reason why this is such a hard question is because there's so many formulas and we don't use them all the time. Like all the rest of the questions, there's like 2 sets of formulas to approach them. And this one has 8 formulas. And we don't use them all every single question. So we don't repeat or reiterate the formulas, so we forget them, I suppose. Or they're just difficult. There's so many of them. IP is equal to X plan. That's the easy one that we're going to be using a lot. We've also got BP, the brake power. This will be terminated to pi n, so T2 pi n. Okay, we're going to have efficiency in here as well, which will be the brake power divided by the indicated power times by 100, I suppose. And then we got the more difficult ones, which are brake specific fuel consumption. Brake specific fuel consumption. I'm going to have to get these formulas out anyway. And then, that's the only one we need. We don't need the other one. So brake specific fuel consumption is not efficiency. So we're going to have units left over. The units will be the number of kilograms of fuel we need to consume to produce a kilowatt hour worth of energy. And that's actually quite easy. The units are going to be kilograms per hour, this is fuel consumption, and then kilowatts, that would be the brake power. So it will be BP on the bottom in brake power, and then fuel consumption, I'll just write mass flow rate in kilograms per hour for that. And it's not going to be too hard. For 3 marks, I think it's going to be quite easy to get. Okay, nice. So let's see what we can do about this and if there's anything spooky. So we're going to do part A first of all, which is going to be IP is equal to X plan. If we have all the ingredients with it, indicated power. Again, there's 2 different ways to calculate all of these. Usually 2 different entrance points. If we need IP and we have all this data, that's great. But we can also get it from the efficiency calculation down here. If we have the efficiency and the BP. I guess no, we're calculating efficiency. So it's going to be quite straightforward. So this is IP is equal to X plan. We're going to be using. Let me just move these guys out of the way for now. I'll pop them over there so we can see everything. And we'll get all the ingredients for this. The IP is what we're calculating. The X is the number of cylinders, which I think they gave us as 6, yeah. The pressure is the IMAP, which is strange because normally we have to calculate it, but they gave it to us as 600 kilonewtons, so 600,000 newtons per meter squared. A newton per meter squared is a pascal, right? So this is just in pascals. So we can just go ahead and write that as pascals. It's fine. I don't know, don't need to cross it out. It's the same as pascals. Okay, the length is the effective length for the stroke, which is given as 150 mil, so 0.15 meters. The cross-sectional area will be that 120 on the bore in millimeters. We need to convert this into meters squared, so I divide it by 2 to get it into a radius, divide by 1,000 to get it into meters, and then square it and times it by pi, because I assume it to be a circle. All right, I'll do this calculation. It's just so I don't have to do a side calculation by in the middle of my calculation, and I'll get that one out in a second. And we got N, which is the number of effective strokes per second. And if it's a 4-stroke, we've got to be careful about it. So N is equal to, let's start with 800 revs. So this is 800 revolutions per minute. Let's drop this down into revolutions per second. So we'll do 800 divided by 60 to get it into per second, and that's 13.33. So this is 13.33 revolutions per second. And then because it's a 4-stroke engine, it says 4-stroke, we're going to divide this by 2. So that turns into how many effective strokes per second. So let's divide this by 2. Okay, that comes out to be 6.666. So this is equal to 6.666, we'll call it 7, and this will be effective strokes per second. Okay, per second. Now we can just multiply it all together. I'm going to calculate the area to start with because I still need that as a number, and I do like to get it on the page just so I can see what I'm doing if I make any mistakes. Square it, times it by pi. Alright, we got that number. And so this is 0.0113097 meters squared, which is nice. All right, now we just multiply everything together. So IP is going to be 6 times by the 600,000. As usual, lots of data in GES 2. Times by the 0.15, times by the cross-sectional area, which is going to be all of this guy over here, and then times by the number of effective strokes per second. So fingers crossed, we can just multiply it all together. I've got my area already in my calculator, so that's nice. 6.6666 times by 0.15 times by 600,000, yeah, times by 6 again, and we'll get 40,000. So the indicated power, the IP, is 4715 watts. 0.0000. Well, that's nice. They don't ever do that anymore. It just completely comes out as like a whole number, which is rare. I think that's just lucky because there's a pi in there. And this comes out to be watts. Okay, so it's 40 kilowatts worth of power. Okay. Just trying to see if I can check that because it's quite a small wattage, isn't it? Like we're used to seeing millions on these. Let's see. It's a 6-cylinder, 4-stroke diesel engine. As the bore is 120 mil. Just making sure I haven't made any. Yeah, it's only 12 mil. Yeah, it's a small one. All right, not bad. And then the cool thing is the brake power. When we do the calculation for brake power, it should confirm this calculation a little bit as well, because hopefully it's an independent calculation. It doesn't rely on any of that data, and it should give us a number that's very similar to the IP, just a little bit less than it. So let's check that. It'll be a nice little indicator if we got it right or wrong. So break power, we're going to use the BP if we can. So BP is equal to T2 pi n. Let's get the question over here so we can see it. I'll just scoot these up and out of the way. Here's the question. So can we get the data from here? The torque is given here as 432 Newton meters, and then we need the number of, okay, so T is equal to 432.5 Newton meters. 2 pi is just 2 pi, not going to change, and this N is the number of effective strokes per second, number of revolutions per second. We don't care about effective strokes for this one. It's a little bit different from that N over there. It's not the same. So we're just going to use this number here really, because this is how many effective strokes, no, how many revolutions per second we have. So let's just pop that in. Okay, so the calculation is now going to be 432.5 times by 2 pi times by 13.333, and hopefully we get a number that's about the same as 40,000. It's going to be about 36, right? It's going to be about 35, a little bit less than 40,000. Let's see what happens. 432.5 times by 2 pi times by the 13.333. Oh yeah, 36, nice. Okay, so we got a good number, which seems like it's about right. So this comes out to be 36233.026 watts. And this is the actual power, the BP, the brake power of the engine, rather than the indicated power, which is the theoretical amount of power. Let's put it in a place where we can see it. So let's put BP is equal to this many watts, 36,000. All right, very nice. Part C is brake specific fuel consumption. Okay, so brake specific fuel consumption, I've already worked out the formula up here. It's just the mass flow rate in kilograms per hour divided by the BP. And let's bring over all the data, which is quite nice because the only thing we got to work out is the mass flow rate, how many kilograms of fuel are we consuming, and it gives us 145 kilograms per day, right? 145 kilograms per day. Let's just say, I'll write this as fuel consumption. And this will be done in kilograms per hour. We need kilograms per second for the efficiency, but this is not the efficiency calculation, so it's all right. So this will be the 145 kilograms per day divided by 24 hours in a day, because obviously, you know, it's running all day. It doesn't say that, but I assume that it is. 145 divided by 24. All right, 6 kilograms per hour. So 6.041666 kilograms of fuel per hour. The BP in kilowatts, well, we just worked out the BP. There it is in kilowatts, so let's write it down. BP will be 36.233 kilowatts. And now we can put that all together. Okay, so the brake specific fuel consumption will be the 6.04 divided by the 36. Okay, we don't really need the units on there. Let's get rid of those. And we'll take our 6.04 divided by 36.233 and 166, or 0. I should say, 0.1667448, and this will be done in kilograms per kilowatt hour. This is how many kilograms of fuel we need to consume to produce a kilowatt hour worth of energy. All right, nice and easy. This is all pretty basically given. Normally these questions are really tricky and really hard, but this time we got lucky. It looks like it's nice and easy. Part D, mechanical efficiency, quick calculation for efficiency. Efficiency will be the brake power divided by the indicated power. This is the actual power divided by the theoretical amount of power, times it by 100 to make it look like a percentage, so we might as well. We'll just get our data from the previous parts of the question, assuming we have not made any mistakes. And like I said, it kind of confirms that we haven't made a mistake because they're similar numbers, which is what we expect. So let's drop them down here. We expect it to be about, like, 80 to 90% efficient basically. Let's see, 36,233. I guess I could put the 0.26 on there, divided by 40, 715, times by 100, 88.99% efficient. So 88.99% efficiency, which is nice. That's part D. It's really straightforward, that question. That's a rare one. Okay, let's look at the next one. This is number 5. A fuel oil consists of 86% carbon, 40% hydrogen by mass, is completely burned for excess of 30% air. Determine the following: the mass of the air required to burn the fuel and the mass of the oxygen in the exhaust. Pretty standard questions, quite short and easy, and not lots and lots of data to work with, so pretty nice. Okay, so we're going to start with the relative atomic masses. Hydrogen is equal to 1, carbon is 12, oxygen is 16, and we're going to say that air is 23% oxygen by mass. Okay, and the first thing to look at is how much carbon. Oh yeah, this question doesn't say how much fuel we're burning. This is a typo on the question, so I'm going to assume we're burning 1 kilogram. We can actually give the answers per kilogram. I mean, I'm sure that's what they meant. They've just never said it this way before, and that's how we can get away with these kind of typos. So we've got carbon, we've got hydrogen. Technically it's not incorrect. Hydrogen and the total. And they've given us the percentages, which is nice. So we got 0.86% carbon. We're going to assume per 1 kilogram. If you look at the most recent paper we just did, we had 0.5 kilograms, right? An awkward number. Okay, the hydrogen will be 0.14 times by the 1 kg. And that, of course, will add up to be, well, 1 kilogram because, well, I don't need to do this total, really, do I, this time? So this will give us 0.86 kilograms of pure carbon. This will be 0.14 kilograms of pure hydrogen. Alright, that's all we need to start with. Now we're going to burn the carbon and we're going to burn the hydrogen. So let's burn the carbon and we're going to burn the hydrogen. Okay, and that's going to be carbon plus oxygen is equal to CO2. And it has to be CO2. Let's balance it out by putting an O2. It does say in the question that it is completely burned, so that's a technical way to say that it doesn't produce carbon monoxide, only carbon dioxide, so it is completely burnt, it's complete combustion. Same thing for the hydrogen. Let's get a hydrogen, add in some oxygen, and we'll make H2O. That's good. Alright, okay, and then we're going to use a little formula of the moles is equal to the mass over the RAM. So we're going to calculate the number of moles, and we're using this little formula because it makes life so much easier for us, because we've got a 1-to-1 ratio. You've got one of these plus one of those makes one of these, and these numbers will always be the same, which is nice. These are really equal to each other, so the amount of carbon that we have is 0.86 kilograms, and carbon weighs, just a single carbon atom weighs 12, that's its relative atomic weight, that's the RAM. And then oxygen is what we're trying to find, and this is O2, which is 2 oxygen molecules, 2 oxygen atoms. So 16 plus 16 is equal to 32, and we're going to solve this little formula. We can do the same thing for the hydrogen over here. We've got 0.14 kilograms of hydrogen. It's H2, so that's 1 plus 1 because they weigh 1 each. This time we're just finding a single oxygen, so it's just 16. And we're going to solve this little formula. We're going to multiply the 32 over to the left-hand side on the first one. So let's do that. I'll get my calculator. And the calculation will be 0.86 divided by 2, no, divided by 12 equals, times by 32 equals, and it gives us 2.293. So this is 2.293333 kilograms of oxygen is required to burn the carbon. Okay, and we're going to do the same thing on the other side. We're going to take the 0.14, divide it by 2, and then times it by the 16. We're just timesing that 16 up to the other side. So 0.14 divided by 2, and then times by 16, and we'll get 1.12. So 1.12 kg of oxygen is required to burn the hydrogen. The reason why we do it this way is because now we can pick out any information we need from these questions. Okay, I'm just going to quickly check this number again because it looks a bit weird, because this one's recurring and this one isn't, so it's a bit suspicious. 0.86 divided by 12 times by 32. Yeah, that's right, isn't it? 0.14 divided by 2 times by 16. Yeah, all right, cool. Just checking. And then we need the mass of air required to burn the fuel. Let's grab the question and bring it down with us, because we are going to calculate from this. From these two numbers, this is the stoichiometric amount of oxygen, the minimum amount of oxygen required to burn the fuel. And we have to do a few stages now of working, because we're going to take this stoichiometric amount of oxygen, work it into the amount of air, the stoichiometric amount of air, then we're going to add in the excess amount of air, and then we're going to work out, oh, that will just be the answer. Yeah, just 3 stages of working on that one. Okay, so let's do those stages. So for part A, then we're going to start with stoic ox. So this is stoichiometric of oxygen. That will be these two numbers. You need this much oxygen and this much oxygen per kilogram, because I'm doing this per kilogram. I'll write that in my final answer because it doesn't say in the question how much fuel we're burning. Stoichiometric is not per kilogram, it's per total amount of fuel. Per kilogram would be specific. Specific means per unit, but not in this case. 2.293333. So this is a stoichiometric amount of oxygen, the minimum amount of oxygen, which is 3.41333 kg. And then we can work this into stoic air. So stoichiometric amount of air, this is the minimum amount of air required to burn the fuel. And this is at 23% oxygen. So we need some quantity of air at 23% is going to give us this 3.4 kilograms of oxygen. Okay, so we're going to work out the stoichiometric amount of air at 23%. We'll do x times by 0.23. This is the total amount of air times by at 23%. It should give us this amount. So how we're going to do this is a reverse percentage calculation. We get x, and that would be the 3.41333 divided by 0.23. It should bump it up. So I'll do that on my calculator. Here we go. I got this 14.84. So we need 14.84 kilograms. It's 0.05, so I guess I could include that. 0.06 kg, and this is the stoichiometric amount of air, the minimum amount of air required, and it's going to be including the excess, right? We should include the excess. So the excess is at 30%. So let's include excess air to ensure complete combustion, and this will be at 30%. So we're going to increase this number by 30%. So I take my original, I will times it by 1.3 or 1.30. That's the 30% right there. And it will make it a little bit bigger. You can work it out another way, but I just like this method. It's nice and quick, less handling of the numbers. So 19.29. So I get my answer to be 19.293 kilograms, and this will be the actual amount of air supplied to the engine, including the excess. That's what they mean by the mass of air required to burn the fuel. Required to burn the fuel. Yeah, is that including the excess? Yes, I suppose it is, right? Because you could burn the fuel without that amount of excess air. You could burn the fuel. This is technically the stoichiometric amount. Technically, is the minimum amount of air required to burn the fuel. This is the actual. So whatever you want. I mean, I'm going to leave it all like this because I'm not trying to understand the wording of the question too much. Really, this is the actual air supplied to the engine, and this is the minimum air or required to burn the fuel. So again, it's a bit bad on the wording. I assume they're saying that we're going to include the excess because that's what was more useful. But they don't say it clearly. Okay, the mass of oxygen in the exhaust. Okay, well, now we've got this amount of air being supplied to the engine. Well, 23% of this air going into the engine will be oxygen. So oxygen in the intake. And we've got to do a little bit of juggling here because the oxygen in the intake will be this amount at 23%. And then we know we're going to be using the stoichiometric amount. We're going to be using 3.4 kilograms of oxygen. So we're going to minus that off. So let's see how much oxygen is actually in the intake. Oh, I should also say, I should write a little note for that last bit. Let's just say, because it's per kilogram, right? So I'm just going to confirm that. So the amount of fuel burnt is not confirmed in the question. The amount of fuel is burnt or burned is not stated in the question. I will assume 1 kg, or we could say 19.293 kilograms of air is required per kg per kilogram of fuel. Of air is required per kilogram of fuel burnt. I think that's just to get me out of trouble. And okay, great. So the oxygen and the intake at 23% would take the 19.2293 times by 0.23. This is the amount of oxygen taken into the engine. So times that by 0.23, we get 4.43. There's a different way to do this, but this is pretty quick and easy. So 4.43, pretty straightforward to understand what's going on. This is how much oxygen is going into the engine. And then we're going to remove some of the oxygen because we're going to use most of it, and it'll be the only oxygen really that's going to be in the exhaust is from the excess air that won't be burnt. So let's see. So we're going to take the intake oxygen minus the burnt oxygen will be equal to exhaust oxygen. Okay, so that's the 4.4 kilograms going in, and then we're burning the stoichiometric amount because this is what we need. It's 3.4. We're not going to use more than that. We're going to use exactly that amount, and that will tell us how much there is in the exhaust. Okay, like I said, we could do it a different way, but whatever. It's not very difficult. This for 2 marks, 3.41333. Get 1.024. So 1.024 kilograms of oxygen in exhaust per kilogram of fuel burnt at the 30% excess, right? Again, they kind of mess up the question because they don't say it very clearly. So that's the best I can do. That'll have to do. All right. Okay, next one, number 6. Describe how vapor compression refrigeration cycle achieves cooling. A standard refrigeration question, no problem there. Just go through your wordy definition. I'm not going to go through those. We're going to go through calculations here. Okay, so let's look at section B now. And section B is electronics and naval architecture. And there's a lot of these simple circuits on here. It would be nice if we could speed up the process a bit. Because the reason why this is a difficult exam, apart from all the ambiguous wording on the questions and the typos, is the number of these guys. These are really slow to go through, and they're very fiddly. You could maybe speed up a little bit, but over the years I haven't really found a better way to do it. If you speed up the process, it makes it less secure as a question. You might make mistakes or typos on it, and that's it's a playoff between the two. It's a balancing act. You want to do speed or accuracy, and I prefer that we go through these questions very slowly and very clearly, and we get the marks, rather than we go through them very quickly and just don't get the marks on them. Because there's 2 of them, because there's 2 of these simple circuits, you can see straight away. I would suggest doing one completely, and the other one you leave as an extra, and I would suggest you do the classic one, the one that you've seen before, which is this one, and we don't touch the new one because the new one's got typos on it. But we're going to start on number 7 over here, which is a classic as well. We've definitely trained on this one. It comes up quite often. It is a nice definition question, really explaining the process of underload, a battery underload. So the first part says that the circuit is a bit like testing a battery that's like a dead battery. You can test it. If you don't test it under load, it can give you a false reading of having a charge, having a voltage, giving a supply voltage, and we'll talk about that more in the classes. But the circuit in figure 7 has a voltmeter shown. When the switch is open, the reading on the voltmeter is 30 volts. When the switch is closed, it drops to 26.67. Explain the reason for the change in the voltmeter readings. Well, we're going to give we're going to state the obvious. We're just going to state the obvious. When the switch is open, there's no current flowing in the circuit, and we get this 30 volt supply, which is the EMF. It's the the EMF of the battery, of the cell, and when it's closed, there is a current flowing, and we get this 26.67 volts, which is the voltage after the voltage drop of this internal resistor. So we can say those two things. Let's quickly write those out. See if we can do it without too many typos. When the circuit is open and there is no current flowing in the circuit, the 30 volt reading is the EMF of the battery, or the cell of the battery. When the circuit is closed, we get a reading of 26.67 volts. We can see there is a 3.33 voltage drop over the internal resistor of the battery. It asks to explain the reason for the change. That is explaining the reason for the change. There's a voltage drop because of this guy. Okay, determine the resistance of the cell. So I think that's okay for 4 marks. We could add up maybe a little bit more detail into it, but 2 sentences is fine. You probably, usually we get 2 marks for a sentence. You've got to say one thing here and one thing here. So I said the obvious. It's obvious to me, it's obvious to you, but let's just make it obvious to everybody else. Okay, determine the resistance of the cell. Well, let's draw out the cell first of all. And we already know there's a voltage drop because of that internal resistor. So this is why it's a nice definition question, because it's quite easy. Let's hook it all up. And okay, so the voltmeter is reading across the whole battery itself, or across the this resistor. This is 24 ohms, and we want to work out the resistance of this guy. We don't know what it is, but we can work out, because we know the voltage across this thing here. This has a, what is it, a 26.67 volt drop across it. So if I draw this in like this, we can work out the current flowing through this this resistor. And then we also know there's a voltage drop over this one as well. This is the 3.33 voltage drop. So let's do those. Once we get the current, we can plug the current into this one to work out its resistance, and then we're done. So let's work out the current in the circuit. So in the circuit, and we're gonna we should really give them names, right? So this is using, we'll call this resistor number 1, and this is resistor number 2. So using R1. Using R1, just so we're clear about it. The thing about these circuit diagrams is I'm going to take my time, go slowly, label everything up nice and clearly, because it's so easy to get confused about everything that's going on. Okay, so we've got resistor number 1, or component number 1. We'll do the VIR on it, and we're going to be using Ohm's law. And maybe, yeah, that's about it really. So the voltage drop is 26.67 volts going across it. The resistance is 24 ohms, so this will be volts and this is ohms. We can use VIR to calculate the I. So I will be V over R, so 26 divided by 24. Alright, so that's going to be, let's see, 26.67 divided by 24 ohms gives me 1.11125, and I use the exact values given because that's the best I can do. So this is 1.11125 amps. Maybe it's a bit overkill on the definition, but it will do. Alright, so this is 1.11 amps going through that section, and because everything's connected in series, we know there's 1.11 amps going through the second resistor. So now we can find its resistance. So find the resistance, I'll just call it, say, resistance over R2. All right, and we're just going to do the same kind of thing. We've got component number 2. We're going to use VIR, and the supply voltage is 3.33. This is the potential difference across that resistor. We talked about that. I did it in my head, because we got 30 volts. If you do 30 minus the 26.67, I'm sure you get 3.33. Let's just double check that. But this is a definition question we've seen like so many times. So it's always the same numbers. They'll probably change it up one day, right? Because they run these questions for so long, and then eventually they start switching them up. Okay, great. Change numbers a little bit. The reason why they use this question so much is because it does demonstrate some key points, but also because it's probably quite a difficult question. People just don't know how to approach it very well. I mean, my guys do. So, all right. Current is going to be this 1.11125 amps going through it. So let's calculate the resistance of this. So VIR, again, a little bit different. R is equal to V over I, 3.33 divided by this number. So we got the 3.33 in my calculator because I just typed it in. Divide that by the 1.11125. 2.996625, so about 3 ohms, but we'll keep it in its definition of 2.9966 ohms as we're working to 5 sig fig. Well, that's 6 sig fig. That's the resistor. That's the internal resistance right there, which is what they want. The resistance of the determine the resistance of the cell. This is the cell, the battery, right? So that's part B. Done. Nice. Okay, next one. Let's get a bit more space on here. Number 8. Now this is going to be quite a long one to go through. Not too long, and like I said, it's a classic question. We've definitely seen it a few times on the past papers, about 4 or 5 times. It comes up a lot. So it's a classic question, nothing new. It's just a little bit of work because of this parallel series section. We've got those embedded systems, and like I keep saying, I'm going to take this nice and slow so we can understand what's going on, rather than trying to do just a mashup of numbers and calculations to speed things up. By all means, you can try to speed this process up, but what I found over the years is that it's, like I said, it's better we go slow and steady and we get the marks, rather than we try to do things too quickly and then we lose it, we make a typo. Usually it used to be that any single mistake would be, I think 1 mistake is half marks and 2 mistakes is like 0 marks basically on the questions. That might have changed. It's been a very long time like that, and I can tell this from my students because you have no feedback on the exams really. They don't give you any marks back, except from your final grade. I can tell that from my students going and taking the exams and then seeing their results as they get back, where they must have made mistakes and stuff like this. So, okay, let's just draw out the circuit. We've got this as 20 ohms, and this is 30 ohms, and this is 24 ohms, and this one's 10 ohms, and this one's 4 ohms, and we're asked to find the current at each of these sections, and it says we've got 32 volts on the cell. So 32 volts. I didn't quite draw the same battery as these guys have, but to be honest, it's my diagram. They don't ask for a diagram in the question, so I can do whatever I want. We're looking for points 1, 2, and 3, which is fair enough. I'm going to call this resistor number 1, resistor number 2, resistor number 3, resistor number 4, resistor number 5, so I can talk about them. And then I suppose we should list out our formulas we're going to be using. We're going to be using resistance in series will be equal to R1 plus R2, and then resistance in parallel will be equal to 1 over R1 plus 1 over R2 as usual, and then we're probably going to be using Ohm's law a lot. Yes, we will. Okay, so those are our formulas ready to go, and then what we're going to do is combine all the resistors together into one big fat resistor, right, as we always do. It's just a bit of a lengthy process. We're going to combine these two together first of all because they're in series and they don't affect the rest of the circuit. Then we'll combine that with this resistor in parallel, and then we'll combine that combination with these guys in series. Okay, so that's the 3 stages we're working on, and okay, so let's combine these two in series. So I said it, I thought it, so I should write it down, just so everyone's clear about what we're doing. Resistance over the series section, and that will be R1 and R2. You don't have to write all this stuff out, but like I said, it really helps to remember and to be clear about what you're doing. Resistance total will be 20 plus 30 ohms. I've already stated my formulas up here, so I think that's just fine. This will be equal to 50 ohms. And now I can redraw my circuit, and this is what takes the time in the exam, because if you draw a scrappy circuit, it's not so clear. You can take shortcuts, and basically the more you practice these questions, the easier they're going to get. So this is now a 50 ohm resistor, and that will be resistor number, well, 6 we can call it. So let's call it resistor number 6. Now we're going to combine these two together in parallel. So let's write that down. Resistance over the parallel section parallel section, which is R6 and R3. Like I said, you don't have to state any of this stuff. You just have to write down your calculations. But I think this makes my life a lot easier. 50 plus the 1 over 24. Just double check my numbers. Yes, that seems okay. All right, so let's add them together and then flip the answer, of course. So 1 divided by 50 plus 1 divided by 24, and we do 1 divided by answer, and we'll get the answer to be 16.216. So the total resistance for that section is 16.216216 ohms. Okay, redraw this diagram one last time. We're not going to need to do any more after this. So now we've effectively combined those resistors together into one big fat resistor with a resistance of 16.216216. Let's call that resistor number 7. And then this is the last section we're going to do because everything's in series. So nice and easy, resistance in series. And this will be R5, R4, and R7, just so we're clear about what's going on. So let's add them together. Resistance total will be the 4 plus the 10 plus the 16.216. What's that going to be, like 30.216? But let's just add them on. Plus the 14, right? 10 plus 4, 30.216. So this is now the total resistance of the circuit, 30.216 ohms. We don't need any more detail. 5 sig fig will be just fine. Okay, so now we can write down circuit information, and this is really my halfway point. The circuit information is going to be VIR. The supply voltage is 32 volts. The total current is what we're calculating, and the resistance of the total circuit is 30.216. Let's use Ohm's law in there to get the current. So VIR, and I is equal to V over R. So this will be the 32 over that 30.216. Okay, so I got this 30.216 recurring in my calculator, so I can do 32 divided by this. Okay, I get 1.05. So the amps flowing through the circuit is 1.059 and change, like 0.3. So I think I can just leave it like this, amps. Okay, this is actually probably one of those questions because they want to know the amps at these 3 points. This point is in series with the cell, so it will have that 1.05. Then what we need to do is work out how the amps will be split over this section, which is actually quite a nice question because we don't have to do a full breakdown like we usually do. But okay, let's just say at point 3, the amps. At point 3, we've got 1.059 amps, which is the total amperage of the circuit. That's just one of the parts of the question, so I thought I'd state it while I'm here. And now we're going to do a little bit of a breakdown. Usually we've got to work our way through the whole circuit and break everything down, but like I said, it's not that bad. There are some shortcuts we can take, and by all means, take them. I'm not going to do that. I'm going to take it nice and slow. So now the question is, the reason why I'm taking this part so slow is because my guys have said in the past that this is the hardest part of the test, basically. It's the part they had the most trouble with. Electronics is a bit strange, it's a bit counterintuitive, it's a little bit complicated. Okay, so how is the current split over the R6 and R3? That's the parallel section. What's going to happen is the current is going to come up here, get to this section, and split over these 2 parts. Oh, in order to get there, my bad, I have to calculate the voltage drop up until that point, because I don't know how many volts are being supplied to this whole section. So we need to do voltage drop. Whoops. And I could do that with, yeah, let's do that with a different diagram, because it's going to be a little bit clearer. I kind of jumped the gun on that. I think it's a little bit of an easy question. So I can reuse my old diagram, and by all means you can use the same diagram. You don't need to redraw another one. So I want to know the voltage drop across these sections, right? We've got 32 volts going in, but each of the components is using up, consuming a certain voltage. So let's calculate the voltage drop over R4, I meant R5, R4, and R7. I don't need all of these. I can just do the voltage drop over R7. This is what I'm looking for. I want to know the supply voltage to this component number 7. That component number 7 is a composite of these two, right? But I'm going to do all of them because I wanted to add up to 32 volts, and it's a nice way to check if I've made any mistakes. It's a little bit extra, a little bit redundant. It's a bit of a redundancy built into the calculation in order to make sure that the calculations are correct. The thing is, we're doing so much calculation over here that we want to make sure we're doing it right. There's no point doing all this and then we make a mistake and we can't tell. It would be nice to be able to tell. So we're going to do VIR for each of them. I don't know the supply voltage for each of these, or the voltage drop across each of the components. I do know the ampage being supplied to them because everything's in series. So there's 1.059 amps flowing through this whole circuit. I can draw it on so you can see it. There's going to be 1.59 volts, 1.059 amps, sorry, going around here, and 1.059 amps coming back into the battery, right, for the whole circuit. So that's what I'm drawing on here, writing on. Here we go. Everything's getting that ampage, which is nice and easy to work with. The resistance is written on the components, which is great. This is 4 ohms, this is 10 ohms, and this guy is 16.216. Using Ohm's law, we can calculate the voltage drop across each of these components. So that's going to be I times by R. Let's just multiply all of these together. Oh, this is an easy one. That will be 10.59 volts. The rest of them I have to do on a calculator. So I got my 1.059. We'll times it by 4. Here we go. This is 4.2361 volts. This is 10.59 volts, and the last one will be 1.059 times by 16.216. This is the one we really wanted, 17.17. 17.17. Was it 27 or something afterwards? 27. 27 volts. So across each of these components, that's what they're using, right? This guy's using 4 volts, this one's using 10, and this one's using 17. If you add up all these voltages, we should get back to 32. So I'm going to do that because, like I said, it's a really nice way to check I haven't messed anything up along the way. Let's just put it where we can see everything. Let's get that over here like this. My calculator. So the 17 volt drop over that last component plus the 10.59 plus the 4.2361. We get 31.99, which is the total voltage. Everything's accounted for. We haven't lost any volts. And we did all this because in the other questions we might need these other values. And I just do it out of inertia for the other questions, but I'm really looking for this one. This is the one we're going to start using on this next section. So now we know that component number 7, that was made from these two put together. So this whole section here, this whole parallel section, is getting that 17.1727 volts. And now my question is, how is the amps split? Okay, so the amps are coming in, we talked about it up here, at the 1.059, but when they get to this parallel section, they're going to split. They're going to go in two different directions. A little bit is going to go through the 50, a bit more is going to go through the 24, and they're going to recombine and come back out at the 1.059 going out. Is going to be 1.059 going in, but the question is, how do they split? And the way we've set this up is really nice because we can just take component number 6, component number 3, and then we can do VIR. Like I said, it's a bit long, but it's nice and clear. And we know supply voltage is 17.17 because they're both in parallel with each other. So this is a supply voltage. The resistance for each one, that's resistor number 6, that's 50 ohms, and this is 24 ohms. And now we can just get the I by doing VIR. So let's see, using VIR, I is going to be V over R. So we're going to divide this. This will be the 17.17 divided by 50. And this will be the 17.17 divided by 24. And we should get the total ampage for each one, and they should add up to be the 1.059 in total. Let's see. So 17.1727 divided by 50 gets me 0.3434. 0.3434, I think it was 54. Okay. Nice. And the other one was divide by 24, right? So let's get rid of that. Put in 24. 0.7155. Okay. Let's get one more digit. We'll call it a 3. So now we've got Going through this section, we got 0.3434 amps. Going through the bottom section, we got 0.7155 amps. And these two amperages should add up to be the total amperage once they recombine at that intersection right there. So let's just add them together and just double check that actually works to make sure I haven't made any mistakes. If I made a single mistake along the way, this shouldn't work, right? And it does, so it looks like it's all good. And this is the end of the question because they just want the amperages flowing through those two sections. So if you get the question, they're asking for what's the amperage going through that top section and what's the amperage going through the bottom section. Because these two components are in series, the amperage will be the same. We could calculate the potential difference across these, but this question doesn't actually ask for it. So it's a little bit nicer because it means we don't have to do the last step. We could do one last step where we calculate the voltage drops across these resistors, and that would be a normal question actually. It's very common to have that. So there'd normally be one more stage of my working right at the very end, but this time we can skip it. So the top one is at 0.1 and the bottom one is at 0.2. So at 0.1, the amperage is the 0.34. We've got a little amperage flowing through that section. Slightly higher amperage flowing through 0.2, which is 0.71553, I think. Or is it 533? Let's double check. 553, yeah, that's good. Checking my calculator. And then at 0.3, we got that as 1.059, which is the total amperage for the whole circuit flowing through it. Like I said, long question to get through, and this is why this exam is a difficult one, because doing all that work just for how many marks? For eight marks is a lot of work. I mean, it's one we've practiced before, but it's a lot of work. Really slows my guys down. And yeah, you could probably speed this up a little bit. I would suggest just doing it a lot of times until you kind of already know what to do. You can find your own way to cut corners here and there. I try not to cut any corners because we want to have a universal technique that will work in new situations for different circuits we've never seen before. All right, so that's the end of number 8. Let's check out number 9. State Lenz's law. So we're going to skip over the definitions and go straight for the calculations. A conductor with an effective length of this big creates a magnetic flux of microwevers when carrying a current of 45 amps at right angles to magnetic field. The force in conductor is 48 newtons. Determine the diameter of the conductor. This should be fine. We're talking about FBIL, FBIL sine theta calculation, and also B is equal to phi over A. It should just be fine. It's just a little bit backwards. It's a little bit of extra algebra for you guys, which I know is a bit of a sticking point. I mean, we got through all that algebra in GES 1, and now we have to do a little bit here. It's unnecessary, and it's not as nice as just having two straightforward questions where it's calculate flux and flux density and flux, which is what we prefer, but whatever, it's not that bad. Let's see, F, B, I, and L. The sine theta, as usual, can be ignored because we're at right angles. Sine of 90 is equal to 1, so no complications there. Let's get the B, the phi, and the A while we're at it on this side. The force on the conductor is 48 newtons. The B is what we're going to calculate. The I is 45 amps. And the length of the conductor is 0.25 meters. So we can calculate the flux density from here. Oh, that's not so bad actually, because it's just a little twist at the end. Usually we're calculating phi, but today we're calculating cross-sectional area. It's not that bad. It's not like starting from it's not completely backwards. So let's calculate this one first of all. This will be 48 is equal to, well, let's call this x. X times by 45 times by 0.25. Like I said, not that bad. Let's multiply that right-hand side together. We get the 45 times by the 0.25 together to get 11.25. So this is 11.25. Let's write it a little bit slower and clearer. And we're going to drop this down underneath it. So 48 divided by 11.25 is equal to x. And that should give us the flux density in Tesla. 48 divided by this gives me 4.2. It's quite high, it's very high. Used to sing about 2.4. 4.2666 Tesla. Double check everything's right, but it is quite a large force. It's 48 newtons, so sometimes this force will be a lot less. All right, that's the first part. So we got that as Tesla. We're going to use that in our second calculation over here. So we've got 4.2666 Tesla. And then they've given us the magnetic flux as microwebers. So that's the phi over here because it's in webers, right? So 480 microwebers. And micro is 10 to the negative 6. So this is 480 times by 10 to the negative 6. We're using milli and micro for small things. Milli is usual, like millimeters, just fine. You're very used to seeing this one. And micro is just the next step down. And that's all we require for the course. Okay, so we want to get the area out of this, and then we're going to work that into diameter just afterwards, right, as a separate calculation. I'm assuming we're working with a coil, so it's a circle, so we're using pi r squared for that one. But let's plug the values into our calculation, and let's just call this x or something. So we're going to have 4.2666 is equal to the 480 times by 10 to the negative 6 divided by x. Okay, and we're going to flip these guys over. There's no calculation to be done except from to swap these guys across like this. Okay, so I've got the 4.2666 in my calculator already. We just got to do 480 times by, I'll just do regular 10 to the power of negative 6, and then we're going to divide that by the answer. And it gives me my cross-sectional area as 1.25 times by 10, 1.125 times by 10 to the negative 4. So the area is going to be 1.125 times by 10 to the negative 4 meters squared. And now we're going to work this into the diameter, right? So this is the pi r squared is equal to all this in meters. Let's just grab all that, and we have to divide it by pi and then actually square root it. So r squared will be this number divided by pi, because here it's a times, and then we'll square root it as well to get the answer. So that number is still, my calculator still, we'll divide it by pi equals, and then we'll square root it because it's so far it's squared, and we'll get the answer. This is in meters for the radius. So now we've got the radius as equal to, I better write my working down. So here's what I just did, like that, and we got the radius is equal to 5.98413 meters, times by 10 to the negative 3 meters, and we want diameter. The question asks for diameter, so we'll times it by 2 to turn the radius into a diameter. So here's my calculator, times it by 2, and the diameter should be about a centimeter across, right? 0.11, because we're talking about solenoids, and these are for injectors, right? For fuel injectors, so they're about the size of your finger, right? So about a centimeter across. So times it by 2, we get the diameter to be 0.011968 meters, which is 1 centimeter across. And that's what we had to work out for the question. Nothing difficult there, really. Nice, easy, 6 marks. And then Lenz's law, well, those definitions are a bit tricky actually to remember. Quite clunky on the wording, but yeah, we might be able to get the 2 marks on that as well. Okay, let's do the next one. This is number 10, and this is a new set of questions, and they're like combined. This top bit, which is a copper conductor, is a little bit clunky, a little bit difficult to work with actually, and for 2 marks it's really not worth it. And then we got part B, which is 6 marks, and it's a lot of work for 6 marks. The total resistance of the circuit might be okay. Total current supplied, that's probably not too bad. The voltage drop across the 800 ohm resistor is a lot of work to get in there just to get that 3 marks. So you might want to do the first little bit if you have time at the end of the paper, but as usual, they're pretty, not usual, but this is a lot of, these are slow and long to get into. And then we got this typo on the paper where it says 250 volts up here, but it says 400 volts in the diagram, so very confusing, because it says the circuit shown has a 250 volt power DC supply, but it doesn't. And then everything else we have to rely on the diagram. So we better assume that's right, I guess, for the diagram. And they don't confirm any other information. If they just hadn't said this, it would have been better, right? We wouldn't have this conflict. So let's do the top part first of all, and this is to do with resistivity of the circuit, or resistivity of materials. So we're going to use that resistivity formula, which I teach it very lightly these days because it doesn't really come up, hasn't come up for years and years. So as it might get phased back in again, so I'll start including it back in the courses. It's not very difficult, but as I was saying earlier, the way they used to do the old questions are so clunky, and this is a little bit better. It's a bit more realistic. It used to be like a kilometer of cable. A copper conductor is 80 meters long, so this is much more realistic about the sizes. It used to be about 1.5 kilometers or a kilometer of cable, and it used to be like iron wire or something like that. The cables were super thin, as in like zero point 0.5 millimeters, which is like telephone weight wire. It's like, if you want to string out a telephone wire to the farm and you want to talk like through communications like that, I mean, we don't do that anymore. So it's a bit strange to have it in the course. So anyway, we're going to be using a copper conductor. So this is going to be resistance is equal to the resistivity times by the length over the area. Have I remembered that right? I don't have a user thing anymore. All right, I think that's right because it makes sense. You gotta times it by the longer that it is, the more resistance you have. The cross-sectional area will reduce the resistance, and this resistivity. Let's just see what we got here. If we can get the ingredients from here. Oh, I can't see everything all at once. Oh, let's make it smaller. Okay. So the length of the conductor I can see. So let's do R, rho, L, and A. The length of the conductor is 80 meters. That's just fine. That's great. Cross-sectional area. Now this is strange. We've got 2.5 millimeters squared. This is a problem because the resistivity is not given in millimeters. The resistivity is 1.77 times by 10 to the negative 8 ohm meters. We need things to be in meters for them to work. So we're going to have to convert this area, this cross-sectional area, into meters. We'll have a look at that in a second, how to do that. And we just got to calculate the resistance of this thing. Right? The only tricky thing is converting then. We just got to plug these numbers in, but you've got to convert this millimeters. We don't do it too often because it's a bit of a sticking point, converting a millimeters squared into meters. We do it occasionally because sometimes we don't have a choice. And I suppose this is one of those times we don't really have a choice. So 1 meter by 1 meter would be 1 meter squared. And then if I put this into millimeters, that would be 1,000 millimeters over here and 1,000 millimeters over here. So that would be 1,000,000 millimeters squared. 1,000,000 is 1,000,000. Okay, so this is our conversion from one to the other. So I can convert my millimeters squared into meters squared if I divide by 1,000,000. I can do that on my calculator, and it's not so bad. Or I can just write down the answer. The answer will just be like dividing by 1,000,000 is the same as timesing by 10 to the negative 6. But I won't just say it. I'll prove it to you. Let's divide it by 1,000,000. And my calculator should just pop it into that format. 2.5 times by 10 to the negative 6. And if you do that quite a lot, you get used to it, but we don't do it too often. So this is like times by 10 to the negative 6 is the easiest way to divide it. So this can now be written as 2.5 times by 10 to the negative 6 meters squared. Now plugging all this into a calculation to get the resistance, calculate the resistance of the conductor, we just, it's a straightforward calculation. Just a little bit of trouble over the conversion just there. So 1.77 times by the 80 meters divided by this guy. All right, and let's see if we get a decent answer out of it. So here's my calculator. I've got that number already lined up, ready to go. Let's use the fraction button to make it look good. So 1.77 times by 10, make it look like it does on the page, to the negative 8 times by 80 divided by 2.5, I could just use the answer, times by 10 to the negative 6. All right, I get 0.5664 ohms. So that's the resistance of the conductor, 0.5664 ohms. Never seen that question before. Don't know if these numbers are correct because I have nothing to gauge it against, but that will have to do. I think it's fine. But again, like normally, you can say, yeah, that feels about right, because when I did a question similar to this, I got a similar answer, but not this time. Okay, we're going to look at part B now, 10B, and this is a new circuit question. Yeah, we've seen it one time before. I think it's come up one time before, but of course we've got this typo on there. So if you see the typo, great. If you don't, well, you just do it, whatever. And I think, yeah, like I said, the schools, they might notice this. They might tell you about it halfway through the exam. a few typos on these earlier, quite a few typos on these earlier papers of this guy about 2023 and 2024. And those papers have quite a lot of typos on them. So what do we do here is I'm going to take the 250 because, well, I don't know. I got to make a decision on one of them. And we're going to work our way through it. Total resistance of the circuit. The problem with this question really is just long. It's not really actually too hard, so to speak, but it's just a bit long. And like I said, maybe there's a process we can speed this up a little bit, but I am sacrificing speed for clarity. In the actual exam, I would suggest you don't do both of these simple circuit questions. You do one to get the marks, and we've already done one, so that was the old classic. This one's a little bit extra, and because it's a new question we haven't seen before, we're not sure about the numbers. We're not sure if we get it right. You know, might make a typo, and won't be able to like see it so easily. With the other ones we've already done, you can kind of go, yeah, it feels a bit wrong. We got this typo on there as well, and it's not worth that many marks. It's only worth like 6 marks in total instead of 8 or 9 or something. So at the end of the day, maybe not really worth it. I'm still going to do it because we can. So this is 300 ohms, 800 ohms, and 500 ohms. I've seen, like I said, this exact copy and pasted of this diagram with an extra resistor on it in another question, another paper. So it might be worth learning it and practicing it. I'm going to set my 400 to be 250 because that's what I'm going to be using in this, because that's what it says in the question up here, even though it doesn't say it in the diagram. So what do? Got to make a decision. I don't know, 250, 400, what's best? About the same really, isn't it? So 1, 2, 3, and 4. Let's label up these guys, and as usual, what we're going to do, no matter what the questions are really up here, we're going to work out the total circuit. So we're going to work out total circuit resistance. So the way we're going to do that is by combining these two together in series, that combination with this one in parallel, and then this one with this one, those combinations with this one in series again, just to give you a heads up. So we're going to go through that process, and this is what we're always going to do. It seems a bit long. There might be a way to speed it up, but I haven't found it yet. I think, yeah, like I said, as always, we're sacrificing speed for clarity, so take it nice and slow, nice and clear. So we said all that stuff, so I'm going to write them down just so I don't lose track of what I'm doing. So this is resistance over the series section, and that will be the R1 and R2, and we're just going to add these guys together. The formula is resistance total will be equal to the R1 plus the R2. Then this is the 300 and the 800. So the 300 ohms plus the 800 ohms, that would be equal to what? 1100 ohms. Probably. Let's get a calculator and just double check that. So, because I don't want to make any silly mistakes on this thing. So 300 plus 800 is equal to 1100. Nice. Alright, so what we have just done is combine those two resistors together into one. So I can redraw my circuit like this, just so we can see it all clearly. This is what takes a bit of time, but like I said, we're sacrificing speed for clarity. And this will be resistor number 5. Okay, next thing to do is going to be combining the resistor number 5 and the resistor number 3 in parallel with each other. So I said it, we should write it down. So this is resistance in parallel. That would be R5 and R3. Okay, we can use the parallel formula. 1 over R total will be 1 over R, well, I guess 5 plus 1 over R3. Let's get the numbers on that. That'll be 1 over RT is equal to 1 over 1100 plus 1 over 1000. And we're going to flip it at the end. So, calculator. And we're going to say 1 divided by 110, 0 plus 1 divided by 1000 equals, and then 1 divided by answer. Quite awkward numbers now on this. Okay, that will have to do 523. So the total resistance for this section is 523.8095 ohms. And just so we're clear about what's going on, I can redraw my diagram another time, and we've combined these two together into a single resistor. So that new resistor will be here, and it will be 523.8095 ohms, and we can call that resistor number 6, just to keep counting up on them. Let's hook it all up. Let's move that ohm out the way. All right, so there's our last step. Now we're going to combine these two in series. So this will be resistance over the series section, and that would be R6 and R4. We're just going to add these guys together. So the total resistance for this section will be the 523.8095 plus the 500, and this will be 1023.8 ohms. All right. So this is now the total resistance of the whole circuit. I could redraw this thing, but I think I got enough diagrams on here really, and it's not very exciting. We actually know what's happening. It would just be a single resistor. But we came here in order to calculate the total circuit information, which is really the ampage around the whole circuit. We got the VIR. We got the supply voltage being 250 volts. We've got the resistance being the 1023. And now we're going to calculate the I using Ohm's law. So I is equal to V over R. So this will be the 250 over the 1023.8095. Awkward numbers on this because it's a new style of question, so they're just random numbers basically. 500 added in. That's what we had before. Yeah, there's our 1023. Then 250 divided by this, we'll get nice 0.244. Oh, nice easy numbers to work with. 0.244186 amps flowing through that circuit. Okay, so what is the question actually asking for? The total resistance of the circuit, well, yeah, we did that. The total current supplied, we did that as well. Let's just write those down at the bottom, just so we can highlight them. Part A, total resistance of the circuit is the 1023.8095 ohms, just so everyone's clear about what we're talking about. The total ampage in the circuit is the 0.2 amps right there. Okay, so that's like, those first two marks are okay to get. Now we're going to get the 800, the voltage drop. This will be the potential difference or the voltage drop across that 800 ohm resistor. It's a bit of a pain to get in there because we're going to have to go through everything. We're going to break it all apart to get in there, which is a lot of work. I'm going to run my diagrams backwards again. What you can do is just use the same diagrams. I would recommend writing on this side and work your way back through them. So I'm going to do that over here. And there's a bit of extra, I'm doing a bit of extra work, a bit of redundant work really, just to double check my calculations because like I said before, it's a pain to come all this way and get typos and mistakes. So I am checking for typos and mistakes. So the first thing we're going to do, and we always do the same thing, is the voltage drop over the series section. So this will be over R4 and R6. You see these guys are in series, which means we know the ampage going through these guys. I can draw the ampage on here. What we're going to do for the ampage and the voltage. So let's do the voltage in red. So here's the voltage. And we'll do the ampage in blue so we can see it. So we just said that the whole ampage going through this whole section right here, going all the way around to the battery again, that is the 0.244186 amps because this is in series. So it's being supplied with 250 volts, but this first component will be drawing a certain amount of voltage, and this will also be taking a certain amount of voltage. And we can calculate each of the voltage drops across these components. Okay, so these two voltage drops should add up to the 250. Okay, so we're going to do that. We're going to have component number 4 and component number 5. I meant 6. And we're going to use VIR on them. And let's see. We don't know supply voltage. Even though it says 250, it's quite confusing. We're actually calculating the voltage drop over these. So the current is definitely 0.244186, and that would be the same for both of them over here as well. Okay, and we know the resistance because it's written on the components is 500 and 523.8095. Great. Okay, so using Ohm's law, we can calculate the voltage using VIR. This will be V is equal to I times by R. We're going to multiply these two numbers together to get the voltages, the voltage drops. So 0.2 in my calculator there already, times that by 500. Okay, 122.09. This will be 122.093, which means there's a 122.093 voltage drop across that first component. And we do the same thing over here. We'll take the 0.244186 times by 523.8095, 127.9. Then this is 127.906. These two things combined should add up to the 250. So it looks like they do, doesn't it? Like, let's just double check it. 127 plus the 122.093 is 250 volts. So all the voltage is accounted for, and I'm doing this just to double check it. You don't need to do all these calculations, but I like to do them because it doesn't cost me very much to quickly bang out another one, and we can tell for sure that we got total voltage is accounted for. We haven't made a single typo anywhere along the way. If we did, this wouldn't work. Like, these numbers wouldn't add up. Okay. So now we've got the voltage drop over these two components. Oh yeah, so this second component here has got 127.906 voltage drop. This number 4 was an original component in the original circuit. You can see it there. And then this number, the number 6 here is a composite, right? It's made from all of this stuff stuck together. It's actually made from these two stuck together. And that's our next stage of working to get in here. What are we looking for? Is we're looking for the voltage drop in there. So we've got to do this. There's not much choice about it really. Okay, so now from here we can see we've got 127 volts is being supplied to this portion of the circuit. If you were to hook up a voltmeter over that section there, over that parallel section, you get 127.906 volt drop across that section. That's useful because from this we can calculate how the amps will be split, right? So every time we get to a parallel section, if you imagine amps are like water, so let's get those volts in red. And if the amps are like water, then they're going to be flowing around here at the supply ampage, and when it gets to this parallel section here, so this was 0.29, was it? 0.244. 0.244 amps coming in. When it gets to this section, it's going to split. A little bit of the amp's going to go this way, a little bit is going to go this way. They're about equal. So they're going to get about 0.12 amps through these two sections. So a little bit of the ampage will go this way, and a little bit of the ampage will go this way, just like water in like an irrigation system. And then they're going to connect together again here, and we're going to go back up to our full supply voltage for the whole circuit, which is 0.244. Okay, 0.244. That's essentially what's happening. And I want to calculate these ones. And it's quite easy to calculate. We're just going to use, let me just get rid of all this so we can see stuff a bit clearer. But we're just going to use VIR. So I said a lot of stuff. Let me write this down. So how is the ampage split over R5 and R3? And we're going to use VIR to calculate all of this. So we've got component number 5 and component number 3. We've got VIR for both of them. The supply voltage is 127.906 volts because they're both in parallel with each other, so they both get the same supply voltage. The resistance is written on the object as 1100, and then 1000. Using Ohm's law, we can work out the ampage. So we're going to use VIR to calculate it. I is equal to V over R, so we can take the voltage and divide it by the resistance. This will be 0.127906 just divided by 1000, and that will be amps. And that's actually what we said earlier. It's going to be about 0.12. And then the other one I'm going to calculate on my calculator should be the corresponding amount, 127.906 divided by 1100. Okay, 0.11. So this is 0.116278 amps. And these two sets of ampages should add up to the total supply ampage, which we said was the 0.244. So let's just see if that really works. Again, just to double check it. I can already see it kind of does, so I don't really need to check it. Probably wouldn't check that in the exam because it adds up perfect. Okay, right, so now we know that there's 0.11 going through this top section. 0.116278, and we got the 0.127 going through the bottom section. That bottom section is an original component, and I still have to break down this component number 5 because it's made from a composite. But I think we're at the end because we're back down to the original diagram, and the question's asking for the voltage drop across that 800 ohm resistor, which is in there, which is what we're about to calculate. This is the last stage of calculation. All right, so last step is what are the voltage drops across component number 2 and component number 1. So this is the voltage drop over R1 and R2. So let's get component number 1 and component number 2. And we write down our VIR. VIR. We know that they've got this ampage flowing through them of 0.11. Right? This 0.116278 is the ampage flowing through that top section, through this 1 and 2. So they both get these ampages. And then we know the resistance because it's written on the object. This is 300. This is 800. We only need the 800 one, and that's what the question is asking. What's the voltage drop across it? But I'm going to do both because they should add up to the supply voltage for this parallel section. The supply voltage for that parallel section was 127. You can see how this is very confusing. We're juggling 2 or 3 bits of data each time. It's just enough to confuse us. That's why electronics is a little bit confusing. Well, very confusing. Okay, so let's calculate supply voltages, or the voltage drop to each of these. So using VIR again, V is equal to I times by R. We're going to multiply these numbers together to get the voltage drops across the components. Let's see. 0.116278 times by 300 is 34 volts. So this first one here is taking 34.883 volts, or it's got that kind of voltage drop across it or potential difference across it. And the other one is 0.116278 times by 800, and we get that as 93 volt drop. This is a 93.0224 volt drop. So this is the answer that we're looking for, and we're just going to double check that they actually add up to the supply voltage for that section, which is 127. So it does look like it adds up, but let's just double check it. 93 plus 34, so 93 plus 34.8834 should up to 127. Yeah, it does. So that's the answer. Oh man, it's so long. Okay, and for what? A couple of marks? 3 marks. The voltage drop across the 800 ohm resistor. Is that really worth it? So part III is the voltage drop across the 800 ohm resistor is 93.0224 volts. Okay, great. Well, that's the end of that question. Long one, and it's a new one as well. So, and the numbers are really awkward. I don't like the numbers in that. The numbers are really screwy. They're all over the place, all these decimals, and also the way that the numbers kind of add up to be almost the same is very confusing. It's not very confusing, but it's a bit annoying. Like the way that this is 100 and 1,100 and this is just 1,000, it means you get very similar numbers all over the place. And that's the kind of questions that the new guy likes to do. He does like to do these kind of tricky questions where you have to be very sure about what you're doing, basically, to do them. And that combined with the typo to start with, well, it's not easy. Okay, let's do number 11. So, next question. Where have we gone? Over here. Let's make some space for it. Okay. Naval architecture, and it's a nice standard one. Nothing spooky here. This will be nice and quick and easy. Determine the mass for 8 marks. It's ridiculous. The amount of marks you can get for this will be almost a one-liner. A solid wooden board compared to the 6 marks we're going to get for doing all that work. A solid wooden board is this big, this long, and it's this big and that's deep, and it sits in water and it floats in water. Take the water density be 1010. Density of wood is this much. Determine the mass of wood that could be supported on the plank without it sinking. So we're going to fully submerge the plank in order to get the maximum buoyancy out of it. Now, there's a lot of discussion on this about if you fully submerge a plank, is it sunk? No, I would say it's not sunk. It's submerged, but it's not sinking. And what we're going to do is fully submerge it to get maximum buoyancy. So there's a couple of statements we can say to start with. We should be able to say the volume of the wood will be equal to the volume of the water displaced. Okay, that's pretty easy to see. All this stuff is actually pretty simple to follow through. It's pretty simple to understand, hopefully. The next thing we can say is that the mass of the wood plus the mass of the extra load should equal the mass of the water displaced. And this will be just at the equilibrium condition, just when it's about to sink, right? So essentially what we're doing is we're loading up this piece of wood with extra weights until it just gets to the point where it's going to sink. Okay, so these are our starting points. So volume of the wood is easy. It's given to us as 4.2 meters. It's 0.3 meters wide and it's 0.175 meters deep. So the volume of wood will be the starting point. The volume of the wood will be the length times width times height, length times by width times by height. I'm just stating my formulas, even though they're pretty obvious. So this will be what well, let's do the length, 4.2 times by 0.3 times by 0.175. Okay, so calculate it. 4.2 times, they like their 42s, don't they? 0. Everywhere. 0.2205, 0.2205 meters cubed. From this we can get the mass of the wood. So the mass of the wood, how much it weighs. We're going to work in kilograms because it's a small object, it's appropriate. This will be using Department of Motor Vehicles, the DMV, or density mass volume, I should say. So the mass will be equal to the density times by the volume, and the density is given as 1010. Oh, that's the water. The wood is given as 710. So it'll be 710 times by that 0.2205. Okay, and this should give us the mass in kilograms. So let's do that on a calculator. Times this by 710. 156.555. So it's 156.555 kg. Very nice. How about the mass of the water displaced? The mass of the water. Now, the water we're pushing out the way is going to be exactly the same size as the wood. So it'll be the same calculation, basically, just with a different density. It'll be mass is density times by volume. The density of the water is at 1010, because it says that in the question, yes. And then the volume will be exactly the same as the wood, so it'll be this one up here. So let's get that number out. Let's see what we get. So the calculation is going to be 1010 times by 0.2205, 222. And this is a classic question. We have definitely done it before, so all these numbers feel pretty familiar. Right, so 222 is the total mass of the water. Now the difference between these two is the extra load that can be supported. That's actually what we set up here, the mass of the wood plus the extra load. I'm going to rearrange this equation a little bit. So let's just keep going down the page. So the extra load, or the load that could be supported, maximum extra load I should say, like max extra load, would be the mass of the water minus the mass of the wood. So let's say that. Extra load would be mass of water, is the mass of the water being displaced, minus the mass of the wood. And the difference between those is how much we could load it up with without it sinking. Yeah? Alright, so it's going to be 222.705 minus the 156.555. Okay, so I've got the 222 in my calculator already, minus 156.555, and we get about 66 kilograms, which is about, after a few days of not eating anything, floating on a shipwreck, you could sit on that plank just fine and get your feet out of the water. So this is 66.15 kg, a comforting thought, I know. 66 kilograms is the extra load that could be supported, and that for 8 marks is very nice, very quick, very easy, and are all pretty intuitive and easy to see what's going on. That was number 11. Okay, let's do number 12. Alright, number 12 is a naval architecture question, but it's a little bit harder. It's not too hard, it's just the harder style, right? This is to do with loading and unloading, or usually it's bunkering and unbunkering fuel, and it's a change of center of gravity of the ship while it's loaded or unloaded. And we've got a few different variations on this, and I think this is the easy one. A ship with a displacement of this much volume in seawater with this density, 2 double bottom fuel tanks, each measuring this size, are equally positioned on either side of the center line. These tanks are filled with a heavy fuel oil. Determine the change in center of gravity G in both magnitude and direction, given that the initial kg is this much. So we've got a table to work this out because we're basically doing moments. I don't think I need to go into all the details of it, but I'll make it understandable. Right, let's do a cross-sectional diagram of the ship first of all, because we've got to draw out these fuel tanks. So these fuel tanks are sitting on the bottom of the vessel. They're not above, they're not sitting like 1.1 meter above the bottom. They are sitting on the bottom of the vessel. Two double bottom fuel tanks measuring this long, this wide. So 5.5 meters is 5.5 meters wide. And then going up here, we are 2.1 meters deep, like this. Are positioned equally either side of the center line. The tanks are now completely filled. Okay, so we're going to be talking about the center of gravity. We do need the center of gravity of those tanks. They are uniformly distributed loads as far as we're concerned because they're completely filled or completely empty. The tanks are now completely filled. This is bunkering. So yeah, it's okay. And then we've got some more information, which is so I could actually write on my center of gravity. I'll do that in a second. We've got the center of gravity of the ship, or keel, the kg of the ship, which is a keel to center of gravity. So that's 3.8 meters initially when the tanks are empty. The reason why I'm a little bit hesitant to fill in all my data is because I want to get to this table. The table is giving me a lot of direction in what to do basically. So all I need to do is remember the table, which is nice because you just fill in the blanks basically. We're going to use the same table that we use in GES 1 for doing the beam questions, right? So the name, the mass, the force, we don't really need this column, and then the distance, because force times by distance is equal to a moment, and then the direction that things are going to be going in, direction. Okay, right, I think that's okay. We could get some units on here for some extra good measure. Let's just drop all these down. So the mass will be done in tons because we're talking about ship-size objects. The force will be, we're not going to use that column. We're just going to do stuff in ton meters. So the distance will be done in meters. The moment technically then will be done in ton meters. That's just fine. And the direction will be anti-clockwise or clockwise. The reason why we're saying that is because if you pick the vessel up and you dropped it on its side, it would be like this. That's what I'm imagining anyway. Okay, and the good news is this table is pretty easy because we don't need the force column and we always use the same objects. We've always got the ship, we've got the load, and we've got ship plus load. And this is what makes it so easy. We're using the same techniques that we used in GES 1 that we learnt very well for doing the beams, but we're using a reduced format, so it's nice and simple. This will be clockwise, clockwise, anti-clockwise, or vice versa, but it's always going to be the ship and the load versus ship plus load. Right, now we're just going to fill in the blanks. Do we know the mass of the ship? Well, no, we don't. We know its displacement and we know the density of seawater, so we have to do a side calculation to work out the mass of the ship. So the mass of the ship will be equal to, we'll use Department of Motor Vehicles, the DMV, again, density, mass, volume. So the mass will be the density times by the volume. They've given us the density of the seawater as 1025 kilograms. I'm going to drop that straight into tons. So it's 1.025 tons per cubic meter. And we've got 6430 cubic meters. So the tonnage will be a little bit higher than 6430. So 6430 times by 1.025 gets me 6590. Okay, so it's 6590.75 tons is going to be the mass of the ship. We can put that into our table, 6590.75. Okay, now do we know the mass of the load? Well, no, we don't. We know the size of the tanks and we know the density of the oil, so we can calculate it. So let's do a calculation for the mass of the tanks, or the mass of the load. The mass of the load. This will be the tanks when they're full, right? The mass of load, and this will be the same thing. It will be mass is equal to density times by the volume. The volume is going to be the length times by the width times by the height of the tanks, and then there's two of them, so we better put a 2 in there. We've got to get all the data for the tanks. Oops, let's just grab the question and put it on the side over here so we can see things a little bit better. How big are those tanks? Well, they are 12.5 meters long, they're 5.5 meters wide, 2.1 meters deep, and then there's two of them. And then the density is going to be 0.968 tons per cubic meter. I'm going to calculate the volumes a little bit separately, just because it breaks things down a bit. So 12.5 times by 5.5 times by 2.1, that's the volume of a single tank, times by 2 to get the volume of both tanks, 288. These numbers look familiar because this is a training question we have done before, and times this by 0.968. So this is the cubic meters of the tank, and we times it by 0.968 in order to get the tonnage of the tanks, or the load, 279. Yeah, okay. Again, familiar feeling numbers. So this is 279.51 tons, and this is the mass of the load. We can put that into our calculation over here. So it's 279. So this will be 279.51. When we load up the ship, because the tanks are now completely filled, these two loads will combine, right? The two masses will add together. So we'll get the mass of the ship plus the mass of the load. So we can take our 279 and add on 6590.75. All right, double checking that makes sense. Yes, adding 200 to 500 is going to be, yes, about that number. Right, it looks all right, no typos. So this will be 6870.26. Okay, now we need to fill in the distances, and this will be the distances about which the mass will act. So really what we're talking about is lifting the ship up, tipping it on its side, and then balancing it like on a pinhead. I'm not going to do that because I don't need to, because after we've looked at it a few times, you just get the idea, and we do that in classes, right? So this distance here is going to be our leverage for the ship while it's unloaded. As we load the ship, I do expect the center of gravity to be lower. This will be the new kg right here. We don't need it right now, but it's just nice to see it's going to go down in this direction. Sometimes we're loading above the center of gravity and it will pull it upwards, but this time we're loading below, so it's going to pull it downwards. This will be the new kg here when we're done. And but the ship itself is acting 3.8 meters away from the queue. So we are, oh, we didn't say that. We are taking moments about the queue. Okay, so I will say that at some point as well. The distance is 3.8. Okay, the distance that the load is acting about will be its center of gravity to the distance to the queue, and that's going to be half of the total height because it's a uniformly distributed load. It's a UDL, right? We're considering the liquid in the tanks to be uniform because it's a uniform liquid for sure, right? This will be 1.05 meters on the height, so that'll be 1.05, which is half of the 2.1. Okay. Then the next bit is we're actually calculating the new center of gravity after the ship is loaded. So this is all the data we need to get from the diagram. Now we can get to work just solving the table. To calculate the moments, we're going to multiply that by the force, the mass by the distance. We'll multiply these two columns together to get this one all the way down. So some of those numbers are quite easy. Like this one is going to be 6870.26x, and the other ones are not easy. All right, so 6590.275, I think, yeah, times by 3.8, 25. Okay, so this is 25044.85, and then the other one, just underneath that, will be 279.51 times by 1.05 to get 293. So 293.4855. Okay, and as usual, we can now say the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. Okay, so let's pop that over here, and then this will be the clockwise moments, this one here, and this one as well is clockwise, so we can add these two numbers together. And then we should be able to make that equal to the anti-clockwise moments, which is this one with the x in it. Okay, add these two numbers together on a calculator. Let's do that. 293 is already in there. We can add in the 25044.85. Okay. I'm going to see everything all at once. 1 second. Okay. So this whole thing adds up to be 25338.3355, and this will be equal to this number still. And then we're just going to divide the 6,000 down underneath it because here it's a multiplier. So we divide it down, and this should give us a new center of gravity, the new kg, which will be a little bit less than the original kg. It should be closer to the q. So divide this by 6870.26. 3.688. Let's see. 3.68811, and this is equal to x, which is equal to the new kg. The old kg was 3.8, and now this is 3.68. Usually, in a lot of the other questions, we have a 5 centimeter reduction. This is a bit more, isn't it? This is like about 11 centimeters or 12 centimeters, so 11 centimeters. which is alright, seems okay. And what do they want in the question? They want the change in position of G, both in magnitude and direction. This is the new kg, so we can say the change. The change will be the old minus the new, or the new minus the old, just the difference between them really. So I could say 3.8 minus a 3.688. I might want to do it the other way around, because it's actually going down, and we can show down by using negative. And they do write it like that in the questions, so we can write it like that in our answers. So there it is, the 0.11, which is 11 centimeters, 0.11188 meters, and this is downwards or keelwards. So we could put a negative in there to show the direction, or we can say it clearly in English. We could just say the change in kg will be 0.11188 meters, and that will be a reduction or downwards or keelwards. Keelwards, these are all different ways to say direction. Yeah, I think that's fine. That's the magnitude. Magnitude means quantity, which is the how much, and direction is keelwards, or we could say downwards. Right, that's the end of it. That wasn't so bad.